Standard interactions with a large language model are ephemeral. You input a prompt, it returns a text string, and the exchange exists as a single linear thread that resets when you close the window. This design fails for persistent engineering workflows or deep data analysis. You cannot manually upload historical context or rewrite operational rules for every new interaction. Building a procedural computing environment requires decomposing the workflow into three distinct architectural primitives. First, the system needs persistent contextual memory. This is handled by a structure called projects. Second, to solve the problem of procedural inconsistency, the system requires a rigid execution layer. This is powered by skills. Finally, the system requires an isolated rendering layer for complex code or UI. This is achieved through artifacts. Treating a language model as a chat box limits its utility. Real performance requires architecting a system of context, execution, and output. We begin with projects. A project is a self-contained workspace that maintains persistent memory across sessions and adheres to customized instructions that govern the entire environment. The primary bottleneck is context capacity. Loading massive datasets quickly maxes out the window. To bypass this, the system triggers Retrieval Augmented Generation, dynamically fragmenting data and pulling only the required blocks. This decoupled architecture scales effective context capacity by 10x without compromising response quality. This transition happens in the background, requiring no manual toggles or user intervention. Beyond storing data, projects require behavioral control via project instructions. These instructions function as persistent programmatic rules. If you define a formatting template or a specific level of expertise, those constraints apply to every interaction within that workspace. Managing these environments across an enterprise relies on a rigid three-tier permission architecture. The foundational tier is can view, a read-only state. Team members can chat with the data and discuss outputs, while the core knowledge base remains isolated from modification. The can edit and owner tiers grant active modification rights, allowing administrators to update source documents and manage access control. Projects overcome the scale limitations of language models by combining a dynamically fetched knowledge base with controlled permissions. They provide a stable data foundation. Having established where the data lives, we must define how tasks are executed. Skills are dynamically loaded subroutines that force the system to follow a repeatable workflow every time. Utilizing skills requires enabling code execution to open a secure, sandboxed computing environment. This is mandatory because skills execute live procedural code. That code runs within a strictly contained boundary, completely isolated from external systems to maintain security. The system provides built-in skills for standard tasks, but organizations can also engineer custom skills to codify their exact internal workflows, like a compliance checklist or a data analysis methodology. These subroutines actually excel at file execution. By operating within the sandbox, a skill can analyze an uploaded spreadsheet and structure that data into a new slide deck. Note a technical parameter here. When processing these external files, the system generates an entirely new version of the file, rather than editing your original document in place. This execution requires zero manual prompting. The system analyzes the request and invokes the correct skill subroutine automatically. This creates a technical division between the two primitives. Projects serve as the static knowledge hubs, storing the data. Skills serve as the procedural machines, executing the task. By decoupling logical execution from static context, skills convert the model into an active computation engine. With the data stored and the logic executed, the workflow faces the final requirement, rendering the output. Presenting complex code directly in a chat stream is difficult to read and impossible to manipulate. The solution is the artifact, an interactive output window decoupled from the conversational interface. When executed logic produces a self-contained output exceeding 15 lines, a programmatic trigger diverts it into an artifact. This layer natively renders complex formats, supporting interactive React components, HTML web pages, vector graphics, and mermaid diagrams. Artifacts are distinct from downloadable static files like PDFs. They are live, interactive elements that run directly within the application window. This decoupling provides a dedicated environment to view code and iterate on UI features, independent of the text stream. Once finalized, artifacts can be published via a live link, making them accessible for external users to interact with or remix. These URLs allow anyone with the link to view the application, even if they do not have a registered account. To protect privacy, published artifacts are never indexed by search engines. Artifacts complete the architecture. They convert raw code generation into an isolated, interactive layer designed for immediate utility. True utility requires all three architectural primitives operating in concert. The pipeline is deterministic. First, a query triggers dynamic data retrieval within the project, forming a contextualized data packet. Second, that packet routes into a specific skill for sandboxed execution, following your exact procedural workflow. Finally, the executed logic crosses the complexity threshold and enters an artifact for interactive rendering. Projects provide the scalable foundation for organizational context. Skills function as the computational engine, enforcing process consistency. Artifacts serve as the interactive delivery mechanism for complex outputs. By mastering these three architectural layers, context, execution, and output, engineers can move past the limitations of the ephemeral chat box and build deterministic AI workflows.